It's me again. I promise that's the last time of the day. And so this is a newborn software that we are still developing. It's still not available, but I'm excited to show what we got so far. And it's for determining Ploidy and aneuploidy. And so far we apply it to our roses. Again, the same thing. Okay. So our beautiful roses have Ploidy that goes from 2x to 10x, the reported Ploidies. The most common is 4. And usually we determine that using methods as flow cytometry, microscopy, or the correlation with the pollen diameter, and sometimes just for breeding experience, like how hard it is to breed that specific rose. And in our collections in Texas A&M, we detected 2 to 5, and we had some that we didn't know, and we would like to know. And all these other methods has some limitations. So we would like also to get another method that could provide us the result more clearly. And we also have been using the axiom array in the roses, the 68K. So we had data for that. We genotyped lots of the samples. And we had been using this data for other purpose, like ETL studies in diseases. And GChem published 2 papers in 2022 and 2023 about this. And we also genotyped our germplasm, the collection. And other people have been using this array. And I could find data available for that, the raw data, in a bioarchive paper that came up this year from the French group. And they had like 287 samples that I also use in this work. And we thought that what convenient would be if we could use axiom array to also estimate the Ploidy of the samples that we don't know the Ploidy. And we have been using, but first we need to understand a little bit, just a little bit of concepts about the axiom array. So we have 2 probes designed for each one of the alleles. And we have like each probe will emit 1 light intensity for each allele. And we capture that X as X and Y. So X for the intensity of one allele and Y for the other allele. And another important measurement here will be the ratio. That would be the Y divided by the sum of both. So in a diploid example, like the homozygous will have only the X intensity, and the heterozygous 50-50, and the other homozygous 0 and 100. Good. This is an example. And we usually use Fit Poly for doing our dosage color. That's a software that works really well. Thank you, Zrulin. And so it's capable of detecting the different doses and call each one of the genotype for us. So here's a tetraploid example. So in my thyroid example, a tetraploid would have other type of a ratio, like other heterozygous categories. And in this example, this perfect example, the diploid theoretically will have 0, half, and 1, and the tetraploid will have 0, 0.25, 0.5, 0.75, and 1. So it would be the ratios that we would expect for this ploid. So hey, yeah, what could be wrong? And then yes, so one thing that Fit Poly does, and also other softwares like UpDog and Supermassa, they do in a population level. So you have a marker, and you get the populations for detecting these dosages. But what happens if one of them have a different Ploidy? So they assume that everybody in that specific spot that you are studying have the same Ploidy. So if one is different, you're not able to detect this with this type of analysis. But then me, what I did is like, so if this is true, this is true. If this is true, I can only just flip it instead of analyzing one marker, all samples. I can get one sample, all markers. Oh yeah, what could be wrong? And then I did it. And then I took one sample that I knew that was diploid, another sample that I knew that was triploid, and another that was tetraploid, and another that was pentaploid. And like the diploid, it's still possible to see, but the triploid is messy. It's definitely, I don't know what is happening here. And pentaploid is even worse. And we can like maybe just change the graphic. So yeah, we can maybe see a peaks, but it's a mess. And maybe other type of graphic. So, so here, this is a graphic that I will use more later than what I will explain. So the ratio is then X in the Y-axis, and in the X-axis is the position in the genome. So for a diploid, I would expect just one heterozygous classes in the half. For the triploid, two heterozygous classes in the 0.33 and 0.66. And tetraploid, the ones that you know also, and the pentaploid more. And we clearly don't see that. And so I start to try to understand what was happening. And what happens that this assumption here, it's not true for data. Like it's not necessarily on zero for each one, for every marker. So sometimes, like, so the dosage here was called by fit poly. And this is the ratio. So you can see like for one marker, and each dot is a sample, individual. So for one marker, one cluster, like the dosage 4, for example, here, it's in 0.75 when it's supposed to be in the 1. And if you see another marker, the same dosage, it's a little bit up, and then in the other one, it's upper, and then it drops again. So each marker has a behavior, a different behavior. So that's why when we flip it, we can see any pattern, because each one of them decide to behave how they decide to behave. And fit poly can detect this because it's by marker. So it just fit the number of clusters. And look, you see, okay, I know what's happening. And at the same time, I went to read things in the human genetics, and they have beautiful graphics. And I said, oh, I want beautiful graphics like this. Like how they do that? Because it's the same type of analysis. It's also XM array. And they are studying like the sex chromosomes. And here's the X that you have the heterozygous, and the Y you have the deletion, that's why you don't have the heterozygous classes. Here's a X and X, so both have the heterozygous. Here's a trisomy, so you have a sample as the X, but you have a extra chromosome here. And also you have like a tetrasomy here, that's 2 copies. You have 3 heterozygous classes. And I was like, I want what they have. And then I went to study their software. So they have a lot of softwares for doing that. The most famous one is called PenSynV. And I tried their software. And one thing that I realized is that they always have, for human genetics, they always have a reference. So when they are studying sex chromosomes, they always have the X. And they use a lot of this analysis for cancer research. And they always have like a reference that's a healthy cell, a cancer cell and a healthy cell. And you need to provide both to the software. And the reason why they do that, it's because they use the samples that they know the Ploidy to standardize the ones that they don't know. So they can keep all the markers in the same position where they're supposed to be, in the axis. So as the example, I can't point here, I need to point from here. Okay. So in the example here, we splitted the samples that they know, the diploids, the references, and they have samples that they don't know. And using this, we can standardize. So if I know that this has dosages of 1, dosage of 0, and doses of 2, I can force them to be where they're supposed to be, and not only use the same standardization with the ones that I don't know. So I'm forcing them to be where they're supposed to be, and doing this by marker, because each marker is different. So I'm expanding to all of them. So cool, I went there, copied their code, And I apply, but in roses, the majority is tetraploid. It's not diploid. We had some samples that are diploids and we knew, so I could test both using diploids as a reference, as they do, but I also expanded this to tetraploids. So I used the same method, but expanded to be possible to use tetraploid as a reference. And I did the same thing. So I call the dosage of the samples that I knew, that were tetraploids, and I applied the same methodology to the ones that I didn't know, and force them to be in the position that they're supposed to be. And this is the difference. So here is a tetraploid sample. This graphic is the one that I show you. That's the position in the genome and the ratio here that now I'm calling BIF after this standardization. And each one of the boxes, it's a chromosome. So roses has 7 chromosomes. And in the bottom, it's a histogram counting the number of dots in the top graphic. And this is for each one of the chromosomes. And here's the total. So considering all chromosomes. So this is using diploids as references. And we can see the peaks. It's good, but it's much better if we use tetraploid as reference because we have more samples and we have more reference too. So yes, closer to the humans graphics. I was happy. And it also works for triploids pretty well, using tetraploid as reference. And because it became clear to see, we start to detect some weird patterns, like, oh, this one here, it's not, it's something that has 4 heterozygous, and between the others that have 3. So it's 5 copies chromosome. So we start to detect aneuploids. And so far, okay, could be just my imagination. But then Oscar went there and did the microscopy for some of the samples to validate the Ploidy capacity, the Ploidy estimations capacities of the software, and done with the matching. And I also was inspired to do a logo with his pictures. And he also did the same for aneuploids, counting +1 or -1. But human genetics, they do more than this. And I want to go further. So far, we are able to detect in chromosome level. So, and humans do locus level. They do CNVs. But for that, they had another measurement. So, for example, here in a normal cell that has heterozygous loci, we will observe what we were observing so far. That's diploids will have 1 heterozygous, and they have another value called log R. That's basically a standardized sum of the intensities. So if it's a normal cell, it would be close to 0. If there is a gain, they expect this log R to be a little bit up. And the BIF is the one that I already show you guys. And if it happens a loss, a deletion, this value would drop a little bit, and we will not have the heterozygous class here. And if we have loss of heterozygosity, homozygous state, we will also not have the dots in the half here, in the heterozygous, but the log R will keep the same because it's heterozygous, it's not a deletion. So this measurement is really important to differentiate these 2 situations here, the loss of heterozygosity and that deletion. Without this measurement, I cannot even think about start to research about CNVs because I cannot differentiate what's homozygous and what's the deletion. And I tried to copy what they do with log R also, and nothing worked with our roses. But we found the solution something much easier. We just apply a z-score by marker, and we could detect a drop in the z-score or sum of intensities, the way we standardize it. Every time that there's a drop, and the BIS. So here's the situation that's a trisom, so loss of a copy, and the z-score also drops. So this is the start of something. We still didn't, so what we need to do now for starting to detect CNVs is to integrate these two measurements, the BAFs and the log R or the z-score now. And humans usually use hidden Markov model for that, and some other software use deep learning, but we still don't know. It's something that we're still investigating. And if you guys have ideas, I'm open to suggestions and collaborations about that. But what we have so far, I implemented in a Shine app, of course, because as you know, I have been showing Shine apps. And so to show and to do analysis automatically in all individuals and to show all these plots. And so we applied this to the roses. Yes, I have time. Okay. And as I told you before, we had some reports of the Ploidies for some of the samples, and we matched with the past report of what we got with Ploidy, and it's about 92% of agreement. And it proves that the method is robust. And the differences, we could not tell if it's Ploidy that's wrong, if the other method is wrong, or if it's just not matching the sample names. Because mostly for the French collection, we were not sure if the past reports was actually the sample that was evaluated. So we actually don't know, but it was only 8%. So it's fine. But it's good too that we could categorize many that we didn't know. And we found about the aneuploids that we had like 7 mapping populations among the samples that we did the detection, deploy detection, and the 2 diversity panels. And the differences of number of aneuploids between them, it's very different. Like mapping populations have more aneuploids than diversity panels, what is expected because the selection panels have more selection and the breeders select them, and probably the aneuploids are not advantaged. So they do not select aneuploids. So from mapping populations, we had like even 24% of the sample having some type of aneuploidy. And in the diversity dependence, 2%. And we also build the maps for the mapping populations and check what happened in the haplotype, in the estimated haplotypes in this type of situation when there's an aneuploid or more copies than expected. So for a regular euploidy chromosome, you will see that poly-oranging or map poly will estimate haplotypes beautifully. You have just a few breaks. But in a situation that we have more copies, it breaks the assumptions of both softwares. So they cannot estimate, so the haplotypes get messy. And the interesting thing is that also always one parent, it's more messy than the other. So here's this parent, that's the same as this parent, and the other haplotype is not as messy. This is an example for pentasome, and this is an example for trisom. So the copy that's have the expected number of copies, it's fine. And the one that has one less copy, it's messy. And then we assume in our analysis that the haplotype that has more breaks, that this not, I don't know if I can call breaks because we know that's wrong, but the one that's more messy, it's probably the parent that donate the gamete, the aneuploid gamete. And considering that, we found that about 84% of the aneuploids that we observed, the gamete came from the mom. What also makes sense because the gametogenesis in the female suffer less selection. And so we explored a little bit more. If we saw that it's more often in our samples that we have a gain of a chromosome than a loss of one. So we have more 5s than 3s. And we also have like differences between the chromosomes. So there are chromosomes like the 1, the 3, and the 6 that have lots of extra or like aneuploids, and the other ones has less. And about the linkage maps, if we have like 3 copies, you will see that the number of recombination breaks will go up a lot. So I counted the number of recombination breaks in the other graphics for all our samples. So they are always a higher number of recombination rates. And this is the euploid, so it's lower. And the pentasomes, the 5 copies. Okay, so of course, if you have like these breaks, these artificial breaks in the map, of course, the maps will be inflated. So we tested what happened with the map if we remove all individuals that are aneuploids, and also removing not the individual, but putting missing data in the haplotype of the chromosome that has extra copies. And in our situation, in all groups, the size of the map will reduce. And we created this function called filter aneuploid that's implemented in the map-poly, that you just put the map-poly object and the Ploidy result. That's just a table saying which ploid is each one of the chromosomes and individuals, and it will filter for you the haplotype. And filtering the haplotype instead of the individual is much better because you filter out less data. So if you consider like the aneuploid individual, you filter sometimes 20% of your data, like in our case, I don't know your species actually, but in our species, will be like 20% of the individuals being filtered out. And if we just filter the chromosome, we just lose like 3% of the data. So it's not as impactful. So the highlights is that we developed a Shiny app that can detect these copy number variations in chromosome level. And we successfully validated this tool with our Rosa's collections. And we are testing for other species and other genotyping platforms. So thank you our collaborators that provided the data. I really appreciated it. And we are thinking about methods to integrate the Z-score with the BIFs to be able to do a locus level analysis. With that, I want to thank you, the group, the Rose Lab people, not only we that you can see here, but also the people that keeps these roses alive and well and pretty. That's Jennifer, Pamela, and Natalie. So I would like to thank you. And I think it.
Any questions for Cris?
Yes. Yes, you.
So you mentioned it was a good talk. So you mentioned about the maternal effect, and also you work with different population. Did you study the parent of different population? Did you find an interesting trend related to the aggregation? Was there like one parent more?
Okay, the question is if there is some differences between the populations in the sense that which parent was donating the gamete, or if one parent has more donation than the other. So yes, we investigated that, and there is no significant difference in the number of aneuploids between the population. That's why I merged everyone in the same graphic, and every time it's the female. So, and we have populations that we switch. So it's like female and then it's the male, and even like that, it's always the male. Always the female. Which individual you said?
In general, we can talk about it later, but
okay.
In general, was the number of progenies with abbreviation that you were giving, was it normal? Was it a random segregation based on your hypothesis, or would there be any specific pattern?
I didn't check. We didn't check segregation of the.
We just check the frequencies of
Yeah.
isomer.
Yeah,
We have
we can check. Yes, yes.
You also have to realize that roses is sort of multi-species complex, so there's a lot of interspecifics. And so there's a lot of weird genetics.
Thank you.
Yes, other question?
So we work with strawberry and we use axle as well. So some of the things that I think we see, especially with some of the older arrays, finding the different subgroups and not to get weird separation and spreading and to that's spreading the acid data. Do you think we could use this tool to identify problematic SNPs on the
I think so, probably. And I need to check better. Yes, so the question is, there's a person here that works with strawberry data with also axiom array, and they face issue depending of how the array was made. Yes.
Design using a diploid and then it's sort of a problematic octopoid reference, and so there are some kind of design issues when we get multiple binding to different subgroups.
Okay, so the array had issues in the design because it was made with a diploid, but it's applied to octoploid, correct? And so if this tool could fix these possible disarrangements. And yeah, we need to check because one thing that I realized that Ploidy can do is, and I was trying to fix that, is that if we have different batches of analysis, like for example, here I had the French and the R data. I couldn't use one to reference the other. So I needed, if it was made like this with these samples, I need to use the reference that were in the same array. So I don't know if it's related, but we need to explore. Yes.
Back
Yes, this question is like, in the last table, you showed that there are some problems, more wrong, wrong, I think that maybe that this whole thing, sometimes different,
So no, we didn't identify differences between the populations. So there are always same amount of number of aneuploids. So the variation was like from 16 to 20. So
the last table is showed what the number of instances of a particular chromosome is involved in an aneuploid condition. That's what we said, that some chromosomes are typically involved in aneuploid, or 50 than others. It is by chromosome across population.
the other one, this one?
We see the 51 on the second line.
Yeah, it doesn't vary that much. It's from 10 to 18. Yeah, it's a lot. Yeah, but it was not significant because it depends of the size of the population too. Yeah. Yeah, but when I did the test, it didn't make difference. But yeah, I can investigate further.